So this is Dean, KK4DAS here. This is the SolderSmoke High School Direct Conversion Receiver project. We'll tune up and down the band. There's the FT8 signals. There's some CW. And you heard the phone section of the band here just a minute ago. So this is the receiver we're going to build over the next few weeks. Just take you through a quick walkthrough here. This is the tuning device. It's a coil that's wrapped around a 3D printed former. It has a brass screw that goes in through it, and you tune by moving the brass screw in and out of the coil. So that's a permeability tuning. The oscillator is a simple single transistor Colpitts oscillator with a buffer transistor. So that forms the VFO. That's going to give us the 40 meter frequency tuning. We should be able to tune across the entire 40 meter band from that. Up at the top here we have the bandpass filter, just a simple double tune circuit that will put us within the 40 meter band and get rid of a bunch of extraneous signals that we don't want feeding in. We take the incoming RF and the VFO tuning through the diode ring mixer, and this produces plus and minus signals, plus and minus the frequencies that come in. The output of that is audio. So out of the audio, we've got a little diplexer circuit here just for matching. Then we got a 3 transistor audio amplifier and a simple speaker. That is the SolderSmoke High School Direct Conversion Receiver. Today, I'm going to talk about sourcing the parts and construction technique, and then next week we'll build the oscillator. So now that we've seen that the direct conversion receiver actually works, let's talk about how we're going to proceed. We're going to build a ham radio receiver. Our goal is to homebrew a build of a ham radio receiver. All the circuits are analog. We're going to use discrete components. We're not going to use any integrated circuits. And we made this choice when we were working with the high school kids because we wanted them one time to build something up from scratch with discrete components and understand kind of the details of putting a circuit together and putting a set of boards together. We wanted to build something that could be understood at a component level. You should be able to know what every component on every board does and get a little bit of experience in circuit and PCB board design. We also told the high school kids that we want to do something that is hard, that it's a challenge, and that most hams will never do this. They'll never build a receiver. We're builders. We're tool makers. So John Kennedy said we choose to go to the moon in this decade and do the other things not because they are easy, but because they are hard. In Homebrew Ham Radio, we do this not because it is easy, but because we thought it would be easy. It is challenging, and we're going to go through some of the challenges. Our direct conversion receiver will be for the 40 meter ham band. It'll tune approximately from 7 to 7.3 megahertz. You can listen to voice, Morse code, FT8, and other digital signals. At one point, this is a real receiver. It's not a toy. You can build a simple transmitter and make contacts with it. You can decode digital signals. In fact, I've done that. I listened to FT8 and just played it into the microphone on my PC and was able to decode the FT8 signals. So while we're not suggesting that you start off thinking about building a transceiver, we're suggesting that you start with the receiver. You certainly can make a double sideband transceiver out of it fairly easily with a little bit of additional work. So what's direct conversion? The signals the receiver will work with are radio waves at about 7 megahertz. Our ears respond to acoustic waves in the air at around 3 to 3,000 cycles a second. We need to convert the radio signals to sound waves that we can hear. So this is done in a single step, thus direct conversion. And that's as opposed to a superhet receiver, which typically does 2 or more stages of conversion. We're going to do one conversion from radio frequency to audio. Here's what the block diagram looks like. On the left, you have the antenna coming in. That goes through a bandpass filter, and the purpose of the bandpass filter is to filter out the entire RF spectrum so that only signals within the 40-meter band come through. The next on the bottom is the oscillator, or the VFO, variable frequency oscillator, or permeability tuned oscillator in our case. That's the tuning mechanism. That is variably tunable from around 7 to 7.3 megahertz. And there's some variability in that as we build it, and we'll go through that when we do the build of the oscillator. Those two things, the RF passing through the bandpass filter and the tuned frequency coming out of the oscillator, are passed to a mixer. And the purpose of the mixer is to combine those two signals and produce an audio signal out. And we'll talk about exactly how that works in the week that we actually build the mixer. The output of the mixer is audio, but it's very low level audio, and it needs to be amplified so that you can hear it in the speaker. So we go through a 3-stage transistor amplifier that amplifies the weak audio signal and drives an 8-ohm speaker. One thing to be aware of, that your RF that's coming in at something less than 50 microvolts is a very, very weak signal. And in order to get it to the point where you can hear it, you got to provide quite a bit of gain, somewhere between 80 and 100 dB of gain. So our 3-transistor amplifier is providing all of that gain. And so that's a critical stage in terms of layout, because amplifiers tend to oscillate and get feedback when they're laid out wrong. So we're going to spend a fair amount of time talking about layout and how to make that audio amplifier amplify and not turn into a runaway oscillator. And from there, it goes to the speaker and to your ears. So that is it. 4 boards: a filter, an oscillator, a mixer, and an amplifier. We're going to build it one board at a time. We're going to test each board before we move on to the next one. And then when we put the boards all together, the high likelihood is your receiver will work and receive. So that's it. Variable frequency oscillator, bandpass filter, mixer, and diplexer. I didn't mention the diplexer before, but the diplexer is just a couple of components that allow you to match the impedance between the output of the mixer and the audio amplifier itself to assure that you get maximum power out of the mixer into the audio amplifier. That's what it looks like when we're done, with a little bit of window dressing around it to mount a volume control and a jack for the power, a switch for the power, and a jack for the antenna. And then a simple speaker. Just about any small speaker will work over there. So that's what it's going to look like, or something like that. The physical layout of the boards isn't all that critical, but it just gives you an idea of what we're shooting for. I want to talk a little bit about how it works. So the bandpass filter, there's lots of radio signals out there, the entire RF spectrum. But we want to filter down to just those within the 40-meter band, 7 to 7.3 megahertz. This lets one band of frequencies pass. It's a band pass, so that's the filter we're using for the receiver, a bandpass filter. As I mentioned before, the mixer is really important. It takes the signal we create in the oscillator and it mixes it with the signal from the bandpass filter. At a mathematics level, a Fourier transform takes place, and at the output of the mixer, we have a sum and a difference frequencies. So if you have a 7.2 megahertz signal, the audio is generally just above that, and you have your 7.2 megahertz coming in from your oscillator. You sum those, and that's over 14 megahertz. Those kind of throw away. We don't need them. But the difference would be the audio that's left over from 3 to about 3 kilocycles, and that is what we're going to amplify. The oscillator that produces the signal we mix with the signal from the bandpass filter. We'll talk about how an oscillator works, but think of it as a cat chasing its tail. A little bit of the output gets fed back to the input. Think of it like a microphone that gets too close to a speaker and squeals. We've all heard that. So also called the VFO, variable frequency oscillator, or the PTO, permeability tuned oscillator. We're using a permeability tuned oscillator in that we're basically putting a brass screw inside a coil and moving it back and forth and changing the inductance and permeability of the coil. And lastly, the audio amplifier takes the weak signals from the mixer, amplifies it to the point where we can hear it coming in from the speaker or headphones. This is the most complicated stage and the one we're going to spend about a time on, as I said, because we want that audio amplifier to amplify and not to isolate. All right, let's talk a little about sourcing parts. On the Hackaday site, there is a bill of materials. Most everything you need for this build is available from Mouser and Jameco. I would ignore the quantities in the spreadsheet. That was done for a large group build. You know, we have hundreds of parts in there. You only need a handful. I do recommend if you can get a group of guys to do this together, it makes it a little easier because, you know, buying 1 or 2 transistors at a time, you end up paying way more in shipping than you pay for the transistors. And for most of the components in here, they're pretty general purpose, and if you do much electronic building, you'll use them. So like when I buy 2 and 3 904s, I buy a bag of 100 of them because I use them all the time. Same thing with small capacitors like the 0.1 capacitors that we use for bypass. I use those almost like eating M&Ms. So a couple of great places to get components. Mouser, of course, is a good source for just about all components, as is DigiKey. I didn't list them here. Jameco has some of the mechanical parts, and they're also a really good source for the trimmer caps that we specify in the bandpass filter. Marlin P. Jones typically has assortments of resistors and capacitors and tuning knobs and switches and things like that, as well as hookup wire, so that's a good place for that. Many of the things you can buy right on Amazon, you can get away with buying basically the assortment cap of transistors, capacitors, and resistors from Amazon and have pretty much everything you need, and you'll have a bunch left over. You can buy on eBay. Be a little careful. Some of the components are sourced out of China and may not be authentic, so be a little careful if you're buying from eBay. Toroids, highly recommend Ketson Parts, run by Hams. Good place to get the toroids, although you can also get them from Mouser and probably Jameco and possibly even on Amazon. Make sure you get the size and mix that we specify. That's one of the critical components. PCB material, I like to use ABC Fab on eBay. Again, he's a ham. He has a wide variety of PCB material. We recommend the CEM material rather than the FR4 material. It's a little easier to use and a little bit less toxic. So those are some good places for sourcing parts. I want to talk a little bit about part selection. And one of the things you learn when you do homebrew is that some component values are typical and critical. And in this case, I'm going to tell you about a couple of them just to kind of hopefully avoid some pitfalls. The capacitors in the PTO, we specify 660 picofarad capacitors. We recommend 330 picofarad micas in parallel. Those are available from Jameco. The values and the fact that they're micas is pretty important to making that PTO stable. If you can't get the micas, you can substitute 330 picofarad NP0 or C0G ceramics. Those are going to be the ones that have no temperature coefficient. They should not drift with temperature. But we've had better luck with stability using the micas, but you can use NPOs or C0Gs there if you can. The audio transformer, this is one where I recommend you do not buy the ones on Amazon. We did. Most of them are mismarked. They're not actually 1K to 8 ohm transformers. Get the ones we specify from Mouser. Save yourself some pain there. Toroid mix, don't substitute different toroids other than what we specified. Trimmers for the BPF, those are pretty important. Trimmer capacitors make it much easier to tune up the bandpass filter. That said, most of the component values are just not critical. For the transistors in the audio amplifier and the oscillator, just about any small signal NPN transistor will work. Although if you substitute too far away from the specs of the 2N3904, you may have to play with some of the resistor values a little bit to keep them working. But 2N3904s are ubiquitous and cheap. For the J310, that's a JFET, just about any small JFET will work. I just bought the 10-pack, I think, most recently from Amazon, and they were by Chenzon, and they work just fine. Most of the resistors and caps within 10% of value are fine. If you don't have the exact values, it's perfectly okay to combine parts to get close to value. Resistors and caps in series are in parallel. So for example, we call out 660 picofarad for the PTO, but I really expect you to use two 330s in parallel for each of the 660s, because that's how we get there. So don't stress out too much on absolute parts. When I got started doing homebrew, I was really very nervous that I had to have every part exactly as it was on the schematic and exactly the value it was on the schematic, and I made it much more difficult for myself than I needed to. So I'll try and give a hint as we're going through each of the boards on where I think you need to pay particular attention to the parts and the components, and where I don't think it's all that important. I'll talk a little bit about construction technique. We're opting for Manhattan style construction. That means we use bare PCBs as the ground plane, and we use pads that are called islands, that are single-sided pads of PCB material that are just super glued to the board, and those are the islands of connectivity. So everywhere there's a junction on the schematic, those get soldered to one of those pads, and everywhere there's a ground, that just gets soldered to the actual board underneath, and that serves as the ground plane. This is a really good technique for RF in particular, because it has that good solid ground plane. We also connect all the boards together with by soldering a piece of solder braid so that they're all at the same ground level. You can use other construction techniques, but for our project and our challenge, I highly recommend that you stick with the Manhattan techniques. Do it once, and then if you want to do something else for a different project or the next build, move on to something else. But I use this all the time. It makes it very easy to work on the board. If you put the wrong component down, you just pop it off, put a new one. If you find you need a new pad in a new place, you just glue one down. If you got a pad in the wrong place, you just pop it off. It is much more forgiving than going through KiCad and doing a PCB layout and sending it off to China and getting your boards back and then realizing, oh, you made a mistake or you got something wrong. So particularly for first-time construction and doing your first homebrew, highly recommend using the Manhattan style construction. We had some questions about, well, how do you get the pads and how do you make them? So, I mean, a pair of tin snips and some PCB material works really well. There was a comment on one of the boards about the fiberglass in the boards. Well, if you're just snipping them this way, there's not a whole lot of likelihood of you getting fiberglass dust in your lungs. If you're using a saw or a CNC machine or something like that, what I do is I wear N95 mask, eye protection, and if I'm using a machine, I use ear protection. If you don't want to mess with making your own pads, you can just buy snap-off meat pads from our buddy Rex, W1REX, QRPme.com. Fun in cans, boxes, and from scratch. Yeah, so highly recommend the meat pads. I use those as well. For PCB materials, I like ABC Fab on eBay. He's a good guy, and he'll custom make pretty much anything for you. Plus, he has lots and lots of boards available. So that's the story on the Manhattan construction. And again, I recommend it for this project. I think we've had a lot of success with building boards this way. So a couple of references for you. We are starting a SolderSmoke Discord server. Big news. There's the invitation link. We'll put it in the notes to the video as well. Our full documentation is on the Hackaday site. High schoolers build a radio receiver. I am gradually going through and updating the schematics on there. I put a new schematic on today that has kind of a revised schematic from our original one that has some of the component values changed, and I annotated a little bit to in anticipation of some of the questions that we're already getting. Bill has a number of videos on the SolderSmoke YouTube channel, and we'll be posting these videos on there as we go. And then, of course, the SolderSmoke blog. When we did the work with the high schoolers, Bill probably posted 20 different blog posts on the build. So that's it for today. Start sourcing your parts. Join the Discord server. Send me any questions you've got. We can start the conversation there. Next week, I will do a video on the building of the PTO, and we'll take it from there. Thanks very much. This is KK4DAS from the SolderSmoke Challenge, signing off.